So, yes, okay. Last but not least, Mike Cates, last speaker of the session from Cambridge.
Thank you very much, and thanks to the organisers for inviting me. So, as maybe some of the other speakers felt a slight sense of impostorship on being asked to speak at a conference about optimal design of complex materials. So what I naturally did was to find something we'd done which vaguely fitted into the title and decided to spin it that way. So, however, I do think behind this is a story which does relate to optimal design in the sense of finding out strategies for designing materials with properties that you might desire. The context is close to what Chantal was talking about in terms of the example that I will give, but the general framework applies to any system which has equations of motion in which are of Langevin type. So anything where I have an underlying dynamics which is stochastic and described by Langevin equations. So I'll tell you the story. I'll start with saying a bit about Langevin equations and how they lead to path weights for trajectories. So although we may be interested in designing materials with certain static properties, largely, what I'll be talking about today actually is materials with certain dynamical behavior that we want to engineer in. So we'll have Langevin equations and path weights, and then what I'll introduce is something which is probably unfamiliar to most people in the audience, which is the idea of filtered or tilted ensembles. So this is the bias dynamics element. So there's ways of starting with a Langevin equation and then biasing the dynamics to achieve a certain outcome. And this is a kind of maximum entropy type of bias that you use. I'll say a bit more about that. Interestingly, there is for each of these bias dynamics, there's some equivalent set of Langevin equations called the driven dynamics, which can in principle be quite complicated, and I will emphasize that point later on. There are ways of studying these biased ensembles using an algorithm called cloning, which I'll also say a little bit about. So the idea with the reverse engineering of design principles is to say, well, let's suppose we have a system, we have a Langevin equation, I want it to do a certain thing which it doesn't normally do. And so I set up the biased ensemble, I construct the driven dynamics, which is a different set of equations of motion that does the right thing, that achieves the outcome that I want, and then I copy the driven dynamics, and that's my design for the revised material, if you understand what I'm saying. So that hopefully will become clearer with an example later on. The example is incredibly simple. It's kind of embarrassingly simple in the sense that it's not telling you anything that you wouldn't guess about the specific instance in question, which is close to what Chantal was talking about with active Brownian particles. And suppose I want, with a set of active Brownian particles, to modify their interactions in a way that will reduce their collisions. So have that at the back of your mind as the target, and I'll just take you to that goal by this rather strange route of setting up the dynamics, biasing it, seeing what the bias dynamics are like, and then copying it. Okay, and I should acknowledge my co-workers here, particularly the first one who's provided lots of the movies for this talk. So Langevin equations. So this is schematic. Overdamp for simplicity, that happens to be the case I'll be talking about later, but it generalizes. So here's a Langevin equation. I have some set of coordinates or coordinate, x, which is a long list in general, a mobility, which is some kind of matrix, and the force, which may or may not be the gradient of some kind of interaction potential. So I have that structure, and then there's a noise term. Lambda here is some kind of unit white Gaussian noise, the usual thing. D is a diffusivity matrix, which tells me how the noise stacks up against these coordinates here. And in systems with equilibrium, with detailed balance, the mobility and the diffusivity matrix are related by a factor of beta 1 over kt. But this is optional. In particular, it won't apply in the active Brownian system that I'll talk about later. And the forces also are only optionally derived from a potential. That also won't apply. So that's a Langevin equation, and I've written it as for one particle, and we'll talk mostly about one particle, but it's a many-body equation in general if x is a sufficiently long list of 3n coordinates. So that's equivalent to a Fokker-Planck equation, which in many ways is more fundamental. which tells me the time evolution of the probability density of seeing the system with a particular set of coordinates, x. So that is this equation here. So here's explicit noise, that's a stochastic, in general, stochastic PDE, we'll see later. This is not stochastic, it's telling me about the time evolution of the probability density. There's an operator here, the Fokker-Planck operator, and it is derivable or relatable to the Langevin equation through a completely understood mapping, which does depend on certain interpretation questions for Langevin equations to do with Ito-Strato discretization, which I don't want to get into, because the primary thing is here. You can think of that as a numerical or a noise way of implementing the Fokker-Planck equation. There's an evolution operator here. PS is the steady state density, so that would be the Boltzmann distribution in any system with detailed balance, but could be the stationary measure of any such operator. What I do is to construct this Fokker-Planck equation, I take a sandwich of this operator here with the stationary measure. And that F it is essentially this F, but has adjustments depending on how I choose to do the discretization or interpretation of the Langevin equation, so that's a technicality. And here is something like a diffusion operator. So, and this phi is anything, but it, of course, this acts on P. Okay, so the fundamental connection between Langevin and Fokker-Planck dynamics is well known, and again extends to many body systems as well as single particles. So what can we say about this? Well, this prescription here, or equivalently the Fokker-Planck description, is equivalent to ascribing a certain statistical weight to a trajectory of the system, to a path, x of t. And x of t, this n is some normalization constant, which you can obviously back out from normalizing things. It's the exponential of an action, and here's the action. What it says is that lambda is Gaussian white noise. So if I take minus mf over to this side of the equation, divide by 2d, then the statistics of x dot minus mf over the square root of 2d is Gaussian. And m being a matrix, I have to be a little bit more careful than that. D also being a matrix, but here is a schematic summary of what happens. So I have an action. Big T here, and throughout this talk, will be a time. It's some long time. I'm interested in this trajectories extending from time 0 to time big T. I have no further need for temperature, won't be using that notation. There's the action. This is the time integral. Typical paths have values of this probability factor here, this action, which are close to the extremum, if you like, the most likely path. And untypical paths have what I will call here large deviations. This has a technical meaning, but it's fine for today. Have values of this action which deviate from the most likely path by terms of order t. So to give some framing of that, imagine that I'm talking about flipping a coin, and I flip a coin millions and millions and millions of times. You know how the Gaussian distribution emerges from the Poisson distribution in the limit of many time flips. But suppose I want to find out the probability that a fair coin systematically over an arbitrarily long period of time is 10% biased in what it does. In other words, throughout it carries on producing 55% heads and 45% tails, although there is no bias. Now that deviation is way outside the Gaussian central limit theorem, but it's a statistically extremely well-defined quantity because I have an enormous number of events contributing to that very small relative probability. So large deviation theory is about that kind of problem. So the kind of problem I'm interested in today with the active Brownian particles is, for instance, I have some active Brownian particles, they do their stuff. What's the probability that they phase separate when they shouldn't, for example? So that's the type of question that this structure addresses. So how unlikely is a consistently atypical trajectory? So I can define something here, which is a sort of atypicality measure. So this is quite abstract, but here I say I take the time average over my long time interval of something, which is a function of the trajectory. It's got a time integral part and something which may be a spatial integral. I have to distinguish these two because for the Langevin equation, I can't just write a dx by dt in here. That gives me problems with the noise. So I think of that as two pieces. And the probability density for this, so say the probability density for finding my 10% wrong head to tail ratio has the following form. It's exponentially unlikely in time, as you can imagine, and there's something called the rate function I of nu. And this is again a completely general structure. So what I can do is I can construct a filtered ensemble, so one in which I have the ordinary statistical weights from the action, which is my basic process, and then I just drop a delta function on that, which says that out of that I just only select the paths which have the desired property nu, say 10% more heads than tails. So this is a set of path weights which are conditioned on the desired property nu, and the delta function there is obviously, it is a filter, and evaluating things with that set of weights with the conditional average is generally not an easy thing to do. But there's an alternative which is part of this the structure that emerges from this large deviation theory, which is to construct what's called the tilted ensemble rather than the filtered ensemble, and that's basically to stick a Lagrange multiplier here. So e to the minus, or e to the plus in this case actually, s times nu. So I get my ordinary path weights, I multiply each by a exponential in the thing I want to actually constrain. That's the tilted ensemble, and one of the properties that emerges in the large deviation limit is that this at large t is equivalent to the filtered one for an appropriate choice of s. Obviously, depending on what value of nu I want to select, here in this Lagrange multiplier I have to choose a corresponding value of s. So that's the tilted ensemble. So under quite broad conditions, which I certainly don't understand fully myself and won't therefore go into, I wouldn't even have time if I did, the filtered and tilted ensembles are equivalent to the large T limit in the same way that in classical statistical mechanics the microcanonical and canonical ensembles are equivalent. It's the same sort of limit, except instead of the thermodynamic limit, in this case we're taking the long time limit at some finite displacement away from the natural value of my parameter nu. And this is very interesting, I think. The tilted ensemble can be directly generated from a Langevin equation. So that's a deep result, which again I'm certainly not going to try to explain. There's an excellent article here by Touchette and Chetrit explaining this in very wide set of conditions, but there are slightly earlier papers in the physics literature that you can look up. So this I can call it a Langevin equation, or I can construct the Fokker-Planck equation for the tilted ensemble. And so here I've just written down, there's this kind of formal but well-defined thing to do. So these are all things that were in the either in the original Langevin or Fokker-Planck equation, Fokker-Planck here, and if you recall, f and g were the things either multiplied by integrated dt or integrated dx in my new integral, which was the kind of thing that is giving me my bias. And that's the Lagrange multiplier. So this is called the driven process for good reasons. It's a proper set of dynamics that gives you directly the biased ensemble of trajectories. Okay, so this looks like a piece of magic that has immense power. We'll see that there's a snag, but let's say a bit more about it first. So if you know about the Doob transform, you will possibly spot that this is some elaborate generalization of it. If you don't know about that, it's close to what I'm going to show with a simple one-dimensional example in a minute, so don't worry about this. It's got a Langevin equation. I told you the Fokker-Planck equation. And it has various properties. It minimizes something called the relative entropy. Well, yes, appropriately defined relative entropy to the unbiased case, whilst achieving the required value of my nu. So, in other words, what this tells you, say, for the flipping a coin, is that if I have my billions of coin flips and I want to find the some rules for how to flipping my what to replace an unbiased flip with to get my 45% ratio, this is the most probable way of doing that. It's the one which does least damage to the statistics of the underlying process. So a minimization of relative entropy, and it also maximizes a tilted action, which is actually makes that link to something called optimal control theory, which is to do with Langevin equations and how you change the drift terms in a Langevin equation to optimally achieve some desired outcome over a period of time. So that makes at least a link to the title of this workshop. And I think there is a real link, actually, which hopefully will become clearer towards the end. So here's an example, movies from Takahiro Nemoto. So imagine a Brownian particle, one particle, in a washboard potential, which is probably barely visible to you here. I'm just tracing it out now. That's the potential. This particle, unsurprisingly, is drifting to the right, but not in a, it's got a barrier to get over each time it comes to a place like this. So there's this one-dimensional Langevin equation. I just scaled out d. That's the forcing. That corresponds to the potential shown here. And the typical unbiased dynamics comprises a diffusive process with a drift to the right, and the diffusion is not, it's not just a uniform combination of those two. You have these pause events when you reach the plateau or local minima in the potential. Okay. So here's some atypical dynamics, and it's very simple what's happening here. This is being biased to achieve a certain average speed to the left, rather than what would normally have occurred, which is a finite average speed to the right. So the bias here is just that integral of the displacement divided by the time. So that's a particular instance of the general structure I described before. And this is some dynamics of delta x, where you see obviously it's now going downwards with time. And it's also pausing. But this dynamics is not very okay, so let's just before saying more about that, let me just say what we have. Okay, so that's our washboard potential. That's u of x. So the typical trajectories are doing the black stuff. The red trajectories are doing this stuff down here. If you work this through, here's the driven process. Now, first thing is, okay, unsurprisingly, there's a force proportional to s. There's also some other stuff here, which involves looking at the eigenfunctions of the Fokker-Planck operator. So it's not trivial how to get the driven process from the fact that I know that I'm, in this case, just biasing the velocity. I have to go through the procedure. Okay. So what you can do, though, nonetheless, is from this equation, you can reconstruct something whose derivative is the total force, including both of these terms, and that's this red dotted potential here. So that's, in the end, because it's a one-dimensional system, I can still think of this as a Langevin diffusion in a certain potential. Instead of the yellow potential that you can barely see, I have the red potential, which obviously is driving the other direction. And this has a particular value of s, which is chosen to give a particular value of the mean speed to the left. Okay. So there's a snag, as you might anticipate from what I said before. That's the recipe, but if I try to do that for a system of many particles with lots of interactions, I get something which is arbitrarily complicated. So obviously I would start with some reasonable, say, pair interaction between my particles, and what I say is, well, okay, well, I introduce this bias to achieve some totally atypical behavior, which is my design target, but in general I get something completely unrealizable in terms of the interactions, and you can't even explicitly construct them without solving the whole problem in a implausible way for any kind of many-body system. So that's an issue, but there is a route at least to generating the ensemble numerically. So I'll come back to the connection with the driven thing in a minute. So I've just written this out yet again. That's the action. Here's my tilt. This is what I'm trying to achieve here for my path weights. And for numerical purposes, I can separate these two factors. One is an ordinary Langevin process, and this is something you do to achieve the bias. You do that by ordinary Langevin dynamics, knowing the simple interactions that you've actually got, rather than these arbitrarily complicated many-body interactions that would emerge, and this you impose numerically by something called cloning, which I will explain in a second. So you separate these two bits in terms of a numerical realization, and this goes back at least to 2006, this general approach here. Oh yes, disclaimer. This is not the only way to do to sample this ensemble, but it's a good one for these purposes. Okay, so what you do, Langevin dynamics with a certain time step on a bunch of samples that you run side by side. So you have multiple copies of the system. Every time increment you look at how these biasing, or the things you're trying to filter or bias, are evolving since the last inspection, and then you produce extra copies of the samples that are doing well. It's as simple as that. You just update your time integrated performance measure, if you like, and you make extra offspring from the samples that are doing well. All the samples have different noise, of course, and then you kill off randomly to bring the total number back down to where it was. So that's a way which you can establish, if you obviously do your numerics correctly, produces this exponential tilt. And it's actually very like a genetic algorithm, but it's very importantly different from a genetic algorithm. There's no genome. I'm just selecting the unlikely paths. I'm not at this stage trying to link that to any recipe, which would be the genome, for the dynamics of those paths. So it looks like things you might have seen in genetic algorithms, but it's not actually one. So here you have your various copies, so this is just an example. So you generate an ensemble like the blue thing here, and that's a way of sampling the tilted or equivalently filtered ensemble directly from the Langevin equation without explicitly having to construct the driven dynamics. And so this is the kind of thing, and unsurprisingly, that sampling gives, and this is just a trajectory chosen. So here you see the cloning going on, and certain things die off and other things survive. And just one realization from that is on the right. So all you need to know is that's an unbiased example of the tilted ensemble, which is produced by the cloning algorithm rather than the driven dynamics that we don't know in general what it's going to be. Okay, so that's all a bit abstract, and so I now want to return to this topic of reverse engineering of design principles. And to do that, I'm going to recapitulate some of what Chantal told us about active Brownian particles, because that's the example that we've done this with. And as I've said as a caveat, this is going to end up as a very simple example which will be almost trivial. And as I also said at the beginning, what I've done here is taken something that we were doing for another reason and spun it to comply with the theme of the workshop. But I do actually think that this is a worthwhile thing to be thinking about in broader terms. So, idea. Start with the unbiased system as an initial quotes design. Choose a target behavior. Realize the driven dynamics which achieves that behavior numerically by a cloning algorithm or in any other way, and adopt the driven process as the new design with the same snag as before. The official driven process has arbitrarily complicated interactions, but if I look at how the system realizes the driven process by just looking at the trajectories that come out of the computer simulation, I may be able to guess something, some relatively simple interactions that can achieve the same effect. And then that's giving me a hint as to how to design or redesign the system to get the target behavior. So that's what I just said here. So see how the driven process does it and try to emulate. So in the Langevin context, that's by using some simple drift terms that give me roughly the same behavior. So back then to the active colloidal suspensions, which Chantal told us about, and also microorganisms, so you can obviously design bacteria as well these days. So these are colloidal sized objects with self-propulsion by some kind of local drive mechanism, bacteria by flapping their flagellae around, autophoretic colloids by doing some kind of biased chemical reaction on the surface of the particle that creates chemical gradients, which then allow it to swim in the presence of a fuel bath. So I'm going to talk mostly about the second of those and try to establish on the way, by the way, that, I mean, talking about designing materials with this type of particle isn't a completely totally science fiction thing to be talking about. Okay, so here's the active Brownian particle picture. So I will be adopting this as the Langevin equations. I'm not going to include any of the more complicated hydrodynamic and other interactions that Chantal mentioned. So here's a particle. It has, in 2 dimensions, it's got a direction in which it's swimming. It has a propulsive speed v. So its angle is being updated by rotational diffusion. And its translational motion has a force term F if there are forces from the exterior with the ordinary mobility mu. There's this self-propulsion term, which we think of as effectively an honorary external force, but note that does not stem from a potential in more than one dimension, because this direction here is path dependent and rotating, and translational noise as well. So I can think of that, the Brownian particles with this constant active force along the embedded U. U updates rotationally, diffusion. And the other thing is that if I put a pair potential in here, and I'm going to talk about active Brownian particles the way we normally talk about them, anything which lives in here as a potential between the particles, as an interaction between the particles, is pairwise, central, repulsive, and not aligning. In other words, there's nothing in active Brownian particles, as written here, that gives you any tendency for the swimming directions of different particles to point the same way. So that's already a hint as to what's going to happen later. So we have that set of Langevin dynamics. Chantal probably showed you this very movie, if not one very like it. I can't remember. So this is what happens with self-propelled particles. The particular ones, you have light control as to whether they're self-propelled or not. You see these clusters, all kinds of things. Let me proceed. So as I mentioned at the beginning, these systems don't have detailed balance, they don't have time reversal symmetry, and they're microscopic or local dynamics, and that shows through not so much when I just have one particle which just does a persistent Brownian motion, which may as well be reversible, but when they interact with obstacles or with each other. So very briefly, if I have these particles interacting with some kind of obstacle, I think of this particle propelling along here, it gets a counterforce from there in the normal direction, it will slide sideways and carry on. If I think of a particle which happens to kick off in this direction, proceeding in the reversed path, it does not slide up here and then zoom off to the right, it just goes past. So it's the interactions that expose the fact that the microscopic dynamics is not time reversal symmetric. A consequence of that, what I've just described with the obstacles, is rectification, which was first seen over a decade ago now with bacteria, where if you put bacteria in an environment with this kind of chevron type boundary between two chambers, then there is a tendency for particles to reflect back to the right and to be more likely to transit left to right than right to left, and you get over time a build-up of an unequal density in these two chambers, which would be impossible for a system in detailed balance unless there were somehow different potentials on either side of this wall. So that's a consequence. The consequence, which Chantal already discussed at some length, was caused by collisions between particles, where two particles which happen to collide head-to-head take a while to rotate and get out of each other's way, whereas if these were coming in the other direction, they wouldn't rotate until they're co-aligned and then come apart. So the latter of these, the interaction between particles, is responsible for MIPS, as Chantal described, motility-induced phase separation. So that's the kind of thing you see on a system, in a system on its way to MIPS. What's next? Oh yes, this is a bigger system also on its way to MIPS. So this is a very well-established scenario, although it does have differences when you look closely with equilibrium phase separation. Okay, so the idea of designing stuff with these particles, here's an example. So I said that in the movie I showed you, that in that particular case, the self-propulsion can be turned on and off with light, and that's actually just because the chemical reaction that makes those particles move requires a photon. It's a photocatalytic. So I can imagine shining a light pattern on a undifferentiated bath of these active Brownian particles, and something interesting might happen. In particular, you can guess the light pattern, and with periodic boundary conditions, this system sets itself up now with a steady state circulating around the boundary conditions with a flux to the right, which is the exact counterpart of the rectification I described before. So that's interesting, because that's something which I could imagine coming in with spatial light modulators and so on, and issuing instructions to my particles and designing some kind of self-assembled object which then has some sort of functionality. So what I'm going to talk about in a moment is nothing like as complicated as this, but I was just trying to establish the idea that controlling the interactions and dynamics of self-propelled particles is a route to designing structures and materials that is worthy of exploration. Okay, so on to my embarrassingly simple example. I showed this slide before. Here's the active Brownian particles, emphasis on non-aligning interactions, so the particles have no torques on each other. And in fact, with these dynamics, if I look at the rotational dynamics of any chosen particle, if you look theta dot, that equation is totally autonomous, doesn't depend on anything. In other words, I can, if you tell me the noise, I can tell you in advance what the angle will be as a function of time. It's totally uncorrelated with anything else. Right, so then I have to decide what to bias. So here's the choice that we looked at in the paper I referred to earlier. It's something which is referred to as the active work. What this does is it measures the work done by the self-propulsion force, essentially against the frictional drag, which is somewhere in here, 1 on the right-hand side. And there's some scaling here which involving the number of particles. But basically, this is something which is 1 for freely moving particles which are always going at full speed, and it's 0 under conditions where the particles are stopped. The force is acting on them, but it's doing no work because they're not having any motion. So what we can do is take the active Brownian system and ask, well, okay, how does it behave if I just filter the dynamics, I just choose the trajectories to observe unusually large or small values of this quantity. So you can think of that as unusually successful activity and unusually frustrated activity, if you like. So on the left, this is the unbiased dynamics first. The left is a particular experimental system different from the one I showed earlier. The only reason for showing this is that the color coding is telling you the direction of motion, and on the right is unbiased dynamics with active Brownian particles coded roughly the same way. That's what we're used to seeing in these systems. If we do the bias towards frustration, in other words, towards little work being achieved by the activity, then you find premature MIPS. You find motility-induced phase separation or something with the same apparent behavior at densities and self-propulsion velocities where you would not normally see it. And that's understandable if you think, well, okay, if I want all my particles to be jammed and not moving, then I should phase separate, because then they'll all be in the same place and they'll be much more crushed together and getting in each other's way, and so W will be unusually small. And then a further movie of this in a minute, showing it at much lower density where it is a much more obviously implausible in the ordinary dynamics. If you bias in the other direction, so towards what is actually collision avoidance, because it's saying each particle successfully moves in the direction that it's trying to go, then you get this. So that's interesting, because what you've got here is what in the local jargon is a dynamical phase transition. You've got long-range order, which is appearing as a result of the bias. So in other words, I have my dynamics of active bearing particles. If I just choose the trajectories which are very, very good at keeping out of each other's way, then even though there's no actual alignment interactions in the original ensemble, those particles align their directions of propulsion. Okay, so long-range polar order. And for those of you who haven't seen this kind of thing before, long-range polar order is something very familiar in active liquid crystalline, or active particle systems, liquid crystalline or otherwise. The thing on the left is actually a mixture of small spherical red particles you can't see being vibrated on a table with these yellow wedges, and that's just an example, one of many, where you see the emergence of at least medium-range polar order in a system which is has active dynamics, in this case caused by the vibration. So we're very used to modeling systems with polar alignment in active materials. There's something called the Vitrek model, which is, as Chantal hinted at with pictures of starling flocks and the like, is a model originally of animals where they look around and see which direction their neighbors are moving in and move in the same direction as the majority of their neighbors. So that's an explicit alignment interaction, which is actually written down there as a kind of update rule. And so this system is behaving as if it had those interactions once you do the bias. Here's a couple more movies at much lower density of the polar and premature MIPS phase accordingly. Okay. So I'm approaching the end of the story. Just as a brief excursion, these are the dynamics, and what we're effectively doing after the filtering is that these noises have now a non-zero mean, which makes them look like a force. In other words, the trajectories biased by the outcome is going to select out from the ensemble of possible noises ones which have statistically unusual properties, like not being zero on average, and then that thing is what turns into, if you like, the drive in the driven process. So effective drift terms at Langevin level. But as I mentioned before, these are in principle some horrible many-body effects in rotational and translational drift forces from the way the bias influences what the noise statistics have to be. Okay, but so as I've already hinted at length, we know how to make a polar ordered phase in 2 dimensions. So suppose my plan is to reduce the amount of collisions between active bearing particles, then I know what to do. I introduce alignment interactions which make them tend to point the same way. So as I said, this is kind of embarrassingly simple as an example, but I do think it is an example. So the logic is choose your target, do the simulation, see how the system has achieved the target, and see if you can think of an easy way of copying it. And this is a case where that seems a perfectly credible route. So flocking in active matter is well studied, and it traditionally has been viewed as caused by alignment interactions, and for sure that's true. But it's also the maximum entropy, in the sense that I've defined, strategy for avoiding collisions in systems without. So, I mean, I could go into a sort of a flight of fancy about how birds evolved to have aligning interactions, that they're just trying to not crash into each other, and this explains starling flocks, but this seems a bit much, really, so I won't go there. Nonetheless, there is, in very simple terms, a design principle there. So, as I say, a bit obvious with hindsight, but I do think that this way of thinking about generating candidates for realizing certain types of target behavior might have a much wider applicability, and it doesn't have to be limited to active matter either in principle. So that was the slide I started with, and I've come to the end of my talk, and thank you for your attention.
Thank you very much. Comments, questions?
I have two questions. I mean, one is hopefully inside the boundaries of your talk, and one possibly a bit outside. The one inside is that if you look at the premature MIPS,
Yes.
where you force the system to achieve a kind of structural arrest, is that at all something you could relate to David Chandler's theory, where he has the transition, considers the glass transition as a first order transition in an extended space with a parameter that couples to the mobility of the trajectories?
Well, it certainly is related in the sense that that approach to the glass transition has used this tilted ensemble, and was doing so, much earlier than this. Though I think, with a different set of questions in mind. So I'm sure there is a relation there, but exactly what that relation is, I don't have a good answer to, but Rob Jack, who's an author on this paper and on papers with David on exactly that, would probably give a better answer than I can, but he's on the plane at the moment.
Okay. Very briefly, then the other question, where maybe the answer is even briefer. I mean, in the beginning, when you talked about the algorithm, you said it looks like a genetic algorithm, but it isn't.
Yes.
On the other hand, if you look at how you evolve functionality in biological organisms, you typically need a sequence of mutations, and you can imagine that there are optimal ways in which you carry out a sequence of mutations, where there's a very natural interpretation of both pruning and enrichment, because you multiply those that are reasonably viable, and you kill those that are less viable. So you think that this might be, again, pointing the way to a strategy to say in which order mutations have to occur to achieve a certain functionality?
I've not thought about that. I mean, yeah, maybe. I mean, the point I was making with the difference with the genetic algorithm, though, is that there's no record of how a particular path got to behave well. It's just been chosen for its good behavior, and what I can't then do is, by having this kind of updated set of instructions in the genome, say, oh, I've now got a good design. So it's different from that. But whether the process of how evolution in that broadly defined sense happens, one can shed light on it with this kind of argument, I'm not sure. I'd have to think about that.
A simple question. If I understand correctly, your filtering mechanism is providing a feedback in the sense of Witzek, the example that you mentioned. I wonder if you can have a situation where instead you can predict what will happen without having the feedback mechanism, like in purely catalytic particles or something like that.
So I'm not sure quite what you mean by feedback.
Well, like you said, you have your birds, and
Yeah.
They know something about their neighbors, and then they decide to go in the same direction. In that sense, they
That sense of
have a
feedback.
feedback.
Yes, I see. Well, I mean, so obviously there must be other strategies for achieving the same outcome. And what I'm not sure is, whether there's any systematic way of generating them. What it seems to me here is you have a systematic way of generating at least one strategy, which has some a priori not advantages, but credibility in terms of this max-end type of picture. But yes, I mean, there must be, for instance, so, maybe I apologize for the simplicity of the polar ordering as a way of avoiding collisions. There are, of course, lots of other ways to avoid collisions, and I can think of local ways to avoid collisions, which just involve every time you approach a particle, you just get out of the way. But that's not what the system does. So it didn't have to use that kind of global long-range order type strategy to avoid collisions. It could have done so in a much more ad hoc local fashion. And it's interesting that actually that's a less likely way of doing it within the unbiased dynamics than the globally ordered one, for reasons which I don't have an explanation for. I mean, the other thing which I thought about, and again, is a flight of fancy way beyond the talk or the conference, is if you think of these particles as drivers in cars, now actually it is a well-known strategy to avoid chaotic locomotion on the road network, to oblige people to drive on one side if they're going in one direction, on the other side in the other, which functions in most countries but not all, as anyone who's been to Mumbai will know. Yeah, so you can think of this as a way of identifying, behavioral nudges in systems which are nothing to do with materials, possibly.
How did you put the mobility, how did you put the light intensity into the picture? Through the mobility or what? No,
that goes in through the swim speed. It's important that it comes in through the rate of propulsion. So in the movies I showed you, which have this photocatalytic chemical reaction process, you have peroxide or another fuel, you've got your Janus colloids, and as soon as you switch off the light, they just revert to ordinary Brownian motion. So if you just imagine having a light pattern where you have a dark chevron and light illumination everywhere else, that's what was in the simulations I showed you. Yeah. There was a hand up over here.
Yes, you made the point about the multi-body result versus this simulating way of producing the result, or the cloning. So how about transferability of your method? So if you want to repeat it for a similar system with, let's say, different coefficients, like would you need to redo the simulation again? Because
I think in general you would. I mean, obviously, you might try some reweighting, but the whole point about the whole problem with sampling the extremes. So what you have is you have your kind of central limit theorem, and you're outside it. So you'll never get enough statistics by doing something unbiased. And there's all kinds of other ways of sampling out there. But in general, if you have introduced the cloning to realize a certain outcome, you won't get enough statistics to do any kind of reweighting of those paths other than maybe infinitesimally shift that. So basically you have to do it each time, and if here you have to do it separately for each value of s, and hence in that backward progress of the one-dimensional particle, for each backward speed you need to do the simulation all over again. Yeah.
But if you had somehow a magic way to know a bit this multi-body interaction, then maybe it would be transferable. And you could.
Oh yeah, well, there's a whole. Okay, so there's a very interesting question behind that, which is, So something I can always do is I can use whatever interactions I can best think of to generate the dynamics, to generate the trajectories, but then use the calculate the weights with the bias. So if, for instance, I had a suspicion about the true nature of the many-body driven thing, I could devise a way of putting that in as a itself as a bias on the paths, and then fix it in the reweighting, which is a bit like what you do with umbrella sampling, things like that, where you can separate the role of generating paths from assigning weights to them. But obviously, if the paths aren't generated with roughly, if you're not in the right region of trajectory space, you will never get the statistics. Yeah.
Any further questions? Okay, so if not, let's thank Mike and all the speakers of the session.